Okay, let's finish off week 11 with this module. So we're going to section 5.2, which will be this module and the next one, the first one next week. So we're looking at the geometry of these autonomous systems. And you remember in module 6, when we looked at section 4.4, we actually found explicit algebraic formulas for the solution of these two-dimensional linear systems where we have constant coefficients. And so today, what we're going to do is because we know explicitly the solutions, we can very precisely say what the trajectories do in the phase plane. Okay, so we're going to assume that the matrices are non-degenerate. The only equilibrium solution then is going to be the origin, 0, 0. And we can figure out the eigenpairs of our matrix. And so it turns out that these split into 6 different cases, which are completely determined by the determinant and trace of our characteristic polynomial for A, right? Because the characteristic polynomial has as its linear term minus the trace and its constant term the determinant. Now you might say, well, why are we doing this? Because we already know how to solve these. The reason is that this is going to give us insight into be able to handle phase planes for nonlinear systems, which are much harder. We don't have explicit solutions, and nonlinear systems turn up a lot. And so that's the reason why it turns out we can linearize nonlinear systems. Okay. So today we're looking at a case where we've got distinct non-zero eigenvalues. Now the reason why we want non-zero eigenvalues is that means that the only equilibrium solution is the origin, 0, 0. Because if we have a 0 eigenvalue, then along that 0 eigenvector, any point on that on the line spanned by that 0 eigenvector will also be an equilibrium solution. We want distinct eigenvalues, because if we have distinct eigenvalues, that guarantees that we have 2 linearly independent eigenvectors. So either both eigenvalues are real, let's say we have R1 and R2, and without this loss of generality, we're going to say R1 is less than R2, or the eigenvalues is a complex conjugate pair, alpha plus or minus beta I. Okay, and so this turns out to give us 6 different cases, 3 for the real eigenvalue case and 3 for the complex eigenvalue case. And really, it all comes down to the sign of the real part of the eigenvalues, right? Because the sign of the real part of the eigenvalues tells you whether you've got decaying exponentials or growing exponentials. Okay, so both in the real case, we can have both eigenvalues being negative, both being positive, or they can have opposite signs. And then in the complex eigenvalue case, we could have negative, 0, or positive real part of the eigenvalues. Okay, so let's look through the cases. Okay, so first, let's look at the case where we've got real eigenvalues. Okay, so we know the solution. So we're going to have, since we've got distinct eigenvalues, we've got 2 eigenpairs, and so we've got exponentials going in the direction of those eigenvectors. Okay, so we need a little theorem. So if we look at the line spanned by an eigenvector, then looking at those lines, every eigenvector for an eigenvalue is going to lie along this line. Remember, if you have an eigenvector, any constant multiple of that eigenvector is also going to be an eigenvector. Okay, theorem. Assume the eigenvalues of A are real. If a line Li lies along an eigenvector of A, then in the phase plane, any solution of x prime equals ax that starts at a point on that line remains on that line for all t. It's going to approach the origin as t goes to infinity if Ri is negative, if the eigenvalue is negative, and it's going to move away from the origin if the eigenvalue is positive. And the proof of that is quite simple. Okay, so we're at some point x naught, y naught. We look at the tangent vector in the phase plane for that point. It's just going to be the derivative, right? So it's going to be A acting on the vector x naught, y naught. Well, x naught, y naught, we're told lies upon that eigenvector, so it's some constant multiple of the eigenvector. Pull out that constant multiple, and we've got the matrix times the eigenvector, and by the definition of an eigenvector, that's just the eigenvalue times the vector. Well, we pull back that constant multiple, and we've got x naught, y naught, and so we've got that it's equal to going to equal the eigenvalue times our original point. Okay, so by that theorem then, once the two eigenvectors are set, the geometry depends entirely on the signs of the eigenvalues. And that gives us our three cases that we saw before. Both the same size, sign, either positive or negative, or opposite signs. Okay, what happens if case one, both negative? So we've got R1 less than R2 less than 0. Okay, so since the eigenvalues are negative, solutions along both those lines tend to the origin as t goes to infinity. So since both of those solutions go to the origin, any linear combination of those solutions is also going to go to the origin. Now, R1 is more negative than R2, so e to the R1t sort of decays quicker than e to the R2t. So as we get closer to the origin, if we've got some non-zero linear combination of those two solutions, it's going to be dominated by e to the R2t because R2 is greater than R1. Okay, so all solutions go to the origin. So the equilibrium solution is a stable equilibrium, right? Because if we perturb it from the equilibrium, it's going to go back to the equilibrium, and we call that a sink. Very much like when we looked at the phase line. So here's an example. So here's a matrix -2, 1, 1, -2. Okay, the sum of the eigen values is -4, and their product is 3. So you do a little bit of math and you can figure out then that means the eigenvalues are -3 and -1. Okay, so they're both negative, and it's very easy to figure out the eigenvectors. For -3 it's 1, -1, and for -1 it's 1, 1. You can double check that. So for this system we predict a stable equilibrium with almost all solutions approaching 0, 0 along that line y equals x. Right, because y equals x is the line spanned by 1, 1. Okay, so we're going to check that by looking at the at maxima. Okay, and so here is our phase plane, and you can see quite distinctly the line y equals x and the line y equals minus x, where the two eigenvectors are. And then if we just start somewhere, so if we're starting near y equals minus x, we're like that. Whereas if we start along y equals x, we see that all the solutions are going towards that y equals x as predicted. And we see all the arrows are going to the origin. Fantastic. Okay, so this is this case with both negative. We saw that that turned out. What about the next case? What happens if both are positive? And so now R2 is greater than R1 is greater than 0. Okay, so both these solutions, both the fundamental solutions are going to move away from the origin as t goes to infinity. And a linear combination of these solutions will also tend to go away from the origin. And so it's just going to look like the previous case with the arrows reversed. So in this case, the equilibrium solution 0, 0 is an unstable equilibrium, and it's called a source, just like we saw in the phase line. So now we have a look at this matrix and comparing it to the previous matrix. You just see that I've just replaced, subtracted minus everything, multiplied by -1. Big difference is that the eigenvalues are now +1 and +3. Okay, so we're going to predict an unstable equilibrium with almost all solutions being the reverse of the previous example. And the reason why I say almost all is, of course, if I stick along the smallest eigenvector, the eigenvector corresponding to the smallest eigenvalue, I'm just going to stay on that line. Okay, so let's go to maxima again, and we can check to see what we see. Okay, and so indeed looks the same. You can see the eigenvectors along the line y equals x and y equals minus x, and all the arrows are pointing away from the origin. And if I go ahead and click the buttons, right, we see that as t goes to negative infinity, we're going to the origin, we're going close to that line y equals x. And as t goes to infinity, we see that we're going away from that, and we're sort of going more towards the line y equals minus x. Okay, and here's the third and final case for opposite signs. We've got a negative eigenvalue and a positive eigenvalue. So solutions along the negative eigenvector tend to the origin, while those along the positive, the eigenvector corresponding to the positive eigenvalue tend to go away from the origin as t goes to infinity. So that means if you have some non-zero linear combination of those solutions, they will also tend to the eigenvector, the line for the negative eigenvalue as t goes to negative infinity, and it's going to go to the line corresponding to the positive eigenvalue as t goes to infinity. Okay, so in this case, we still have an unstable equilibrium, and this is called a saddle point. And that line L1 is called the separatrix because it separates solutions that go in different directions. You can see that quite easily in the example we're going to look at. So here, for example, is we have the matrix 0, 1, 1, 0. And hopefully you can see that it has eigenvalues 1 and -1, right? 1 plus -1 is 0, which is the trace of that. The determinant of that is -1, which is the product of those eigenvalues. And there are the eigenvectors there. We predict an unstable equilibrium with almost all solutions approaching y equals x as t goes to infinity, right? So that's y equals x corresponds to 1, 1, which is the 1 eigenvector, and it approaches y equals minus x as t goes to negative infinity. And the line y equals minus x is the separatrix. So let's check with maxima. Okay, here's our phase plane. Again, you can see y equals x and y equals minus x is the corresponds to the eigenvectors. And for y equals x, we're going away from the origin, and y equals minus x, we're going towards the origin. And so if I just give you a few examples here, we see why y equals minus x is a separatrix, because anything to the left of that, all the solutions sort of go towards the lower left corner, and anything to the right of the separatrix, all the solutions go to the upper right corner. Okay, because they want to go towards that line y equals x as t goes to infinity. Okay, so we've taken care of the case of real eigenvalues. Let's have a look at complex eigenvalues. Okay, so we have one eigenpair, and its complex conjugate is the other eigenpair. So the solution is what we see there. It's an exponential times some combination of trig functions times u and v, where u and v are the real and complex parts of the eigenvectors. This is difficult to kind of understand what it's doing, so we're going to do the same trick as we did when we looked at harmonic motion. We're going to write it as a single trig function. And so if you do that, you get a simpler expression there. We introduce r and phi. So r is square root of c1 squared plus c2 squared as before. And r times phi should equal c1, and r times sine phi should equal c2. And that gives it to us. And that is easy to comprehend, because when alpha equals 0, that equation is a parametric equation for an ellipse centered at 0, 0. Remember, ellipses have two foci, and if you look at the midpoint between the two foci, you get the center, and that's 0, 0. And so you've got lots of different geometry associated with the ellipses, right? You've got major and minor axes, you've got how they're oriented, and you can have where that goes clockwise or counterclockwise. But the main difference in geometry comes from the sign of alpha, in that remember e to the alpha t, right? You're multiplying by an exponential. It's the sign of alpha, which gives us our three cases. So what happens when alpha is 0? Then the solution will be concentric ellipses about the origin, because I told you that fact before, that parameterizes an ellipse. It's going to be period, and the period is 2 pi divided by beta. Okay. The equilibrium solution, the origin, you can call it stable. We don't really like to call it stable. It's non-asymptotically stable, right? So we like our stable solutions to be asymptotically stable, so that you perturb it and it goes back. Here, you perturb it and it stays the same distance away. But this kind of equilibrium is known as a center. So here's a classic example, 0, 1, minus 1, 0, which has those eigenpairs plus or minus I. And in fact, in this one, the solution curves are going to be circles. So we predict concentric ellipses about the origin. Now, is it going to go clockwise or counterclockwise? Well, if we look at what happens to the point 1, 0, we hit the vector, tangent vector 1, 0 by 0, 1, minus 1, 0, and it goes to 0, minus 1. So, right, so 1, 0 is the point, which is the rightmost point on the ellipse. The vector 0, minus 1 is just pointing directly down. So this means we're going to be going clockwise. Okay, and so let's check that with maxima. Okay, here's our phase plane, and as predicted, we're seeing nice circles. So in fact, if I click, you can see that, and we're going clockwise. Yay! So that was a pretty easy one. Okay, and a module question for you is, the first one is, what solutions would you guess for this matrix, 0, minus 1, 1, 0? So just double check that it has the same eigenvalues and then figure out which way it's going to, where the tangent vector is going to go. Okay. So we don't really need the eigenvectors, so I'm not going to show them anymore. I'm just the eigenvalues is all we need. Okay, so what happens if the real part is negative? Solutions will still cycle periodically around the origin, but we're multiplying by a negative exponential, so the amplitude of these cycles is going to decrease exponentially as t goes to infinity. Okay, so in this case, the origin is a stable equilibrium. We have no qualms about calling it that. And it's called a spiral sink. So, new terminology here. So for example, we have the matrix minus 2, minus 1, 2, 0. It has eigenvalues minus 1 plus or minus I. So the real part is minus 1, so we're multiplying by that exponential e to the minus t, and the imaginary part is I, so we've got sines and cosines. So we're going to predict some kind of decaying ellipse about the origin. The tangent vector through 1, 0, so we do the same trick before. We go to like 3 o'clock on the clock at the point 1, 0. We hit it with that matrix and we see we get the tangent vector minus 2, 2. So minus 2 does what? It's going inward on the x direction and it's going upward in the y direction. So it's going to go counterclockwise. Okay, so let's check this with maxima. Okay, so, right, so we're definitely seeing some kind of spirally thing going along. We're not seeing any stable lines whatsoever. And we click. And we're seeing some sort of spiral and it's going in a counterclockwise direction as promised. Fantastic. Okay, and so a similar kind of question. I just changed the matrix a little bit. Minus 2, 1, minus 2, 0. What do you think the solution is going to be? Check the eigenvalues. Check whether it's going clockwise or counterclockwise. Or I keep on wanting to say anti-clockwise because that's what I was brought up to say. Okay, and then finally, let's have a look at the real part being positive. Again, they're going to cycle periodically about origin, but now the amplitude is going to increase exponentially as t goes to infinity. So this is going to be like the previous case, except the arrows are going to go the other way. Okay, the equilibrium solution is an unstable equilibrium, and it's called a spiral source. And so I took the matrix from before, right? Before I had -2, 0 being the diagonal. Here I've got 2, 0 being the diagonal. What that changes is that the real part changes from -1 to 1. So again, so this time we're multiplying by e to the t, and we've got sine and cosines. Okay. So we're going to predict expanding ellipses about the origin. I do my same trick before. I take the vector, I go at the point 1, 0. I look at what the tangent vector is. I hit 1, 0 with that matrix 2, 1, -2, 0. I see I get 2, -2. So it's going out in the x direction and it's going down in the y direction. So it's going to go clockwise. So again, I'm going to check that with maxima. Okay, and here is what the phase plane looks like, and I do the same trick. I look at some solutions, and it's spiraling out from the origin, and it is indeed looks like it's spiraling clockwise. Fantastic. Okay, so finishing up this module, I have one last question. So let's just say we have a matrix A, B, C, D, and I tell you that it's got complex eigenvalues. Okay, so for a second, think about why that means that both B and C have to be non-zero if we've got complex eigenvalues. Okay, how would you predict whether the solutions go clockwise or counterclockwise? Okay, and that's our module.